This is red. That's how you and I refer to this visual sensation. Physically, this is an electromagnetic wave oscillating at around 475 terahertz. This frequency sits comfortably in the visible spectrum of light, around 380 to 750 nanometers long. But color is what happens when the frequency hits your biology. Your eyes detect color with three types of sensors called cones. One peaks around 420, another 530, and a third around 560. When light enters your eye, each one responds with a different intensity depending on the wavelength. Your brain compares those three measurements, and from that comparison, it assigns what you experience as color. This is a red LED. If I shine this into my eye, it's going to stimulate the long wavelength cones the most, and I will perceive red. Now this is a yellow LED. If I shine this into my eye, it's going to stimulate both medium and long wavelength cones. Because at the yellow wavelength, the sensitivity curves of the eye overlap at that point. Well, since a bit of red cones and a bit of green cones are stimulated to perceive yellow, what if we combine red and green light independently? In a 4-pin RGB LED with 3 separate sources, I can turn on red, green, and if I turn on both, then it becomes yellow. Same principle with cyan. I can mix blue and green LEDs together. They stimulate short and medium wavelength cones in the same ratio as a single cyan wavelength would. So the rule seems simple. Red and green gives yellow, a color in between them. Green and blue give cyan, also a color in between. So what should red and blue give? If the pattern holds, it should be something between them. No single physical wavelength does that, but your brain doesn't care, and it invents a new color. Magenta. Okay, so this is nothing new. Blue and red is magenta. So here's blue and here's red. Where's magenta? It's clearly red and blue. Those signals stay separate because they're in different locations. So how close do they have to be so it's perceived as a single color? We can calculate this using a visual angle formula. The red and blue LEDs are separated by 1 centimeter, and I'm looking at them from around 10 centimeters. Plugging in the values in these equations gives us around 5.7 degrees. The human threshold for color mixing is around 0.01 to 0.03. Therefore, 5.7 is far too high, and hence I see separate light sources. So how do we force separate LEDs to converge below this angle? Well, method 1 is packing them closer together. Your phone screen does this. Every pixel is 3 LEDs, red, green, and blue, spaced about 25 micrometers apart. At a typical viewing distance of 30 centimeters, that's about 0.005 degrees, way below threshold. Another method to manipulate this equation is to increase the viewing distance. Instead of forcing the LEDs closer together, I can walk away. For this experiment, I placed 2 LEDs 1 centimeter apart. How far do I have to stand before they become one? Well, at 1 meter, the viewing angle is 0.57 degrees. And for me, they're clearly separate. As I walk backward, here I started seeing obvious mixing. At around 30 meters, the angle drops to 0.019. And you can start clearly telling it's magenta. Easier thing to do would be to just point LEDs at the wall. Every point on the wall surface scatters photons from both LEDs, and when I look at the wall, I'm seeing thousands of surface patches, each emitting both colors from the same spot, and I see magenta. Originally, this exploration started as a color mixing soldering kit. I could have added a 4-pin RGB LED, 3 sources in one package, but then you cannot see the 3 distinct emitters. The mixing is hidden and it just felt like cheating. Using 3 discrete LEDs was a must, so I designed this PCB. I thought I could simply reflect the light off the PCB's white silkscreen, let the board do the scattering, but I could not get the geometry right and the external light interfered too much. All I had to do was to just 3D print a diffuser, a holder, and assemble everything together. The way it works is very simple. Light enters, it scatters, it bounces off the internal surfaces, it reflects off the white center, and with 3 potentiometers, I can control the intensity: magenta, cyan, yellow, white. Right now, right this second, terahertz of electromagnetic radiation is slamming into proteins of my eyeballs, and my brain, sitting in total darkness with no sense of the outside world, is making sense of it. My brain invents color like magenta that don't even exist. There are dimensions of reality I'm completely blind to, and for what I can see, my brain is making it up.